Good evening, everybody. Let's get started. Another day, number 2. Let me start recording on the cloud. All right, I've started recording it. So we are about to review, we should have reviewed lecture 1 at this point. So is there any question? I haven't seen any question on the discussion page so far. Okay, let me then take a poll. There's a 2-question poll. Let's take it quickly. So it says I'm launching the poll. First question is, have you watched the lecture videos and read lecture notes for today's topic? Another question that, have you noted your queries in corresponding discussion page? I got so far one answer on the notes. Let me see. Module 1. Hey, why don't I see any question there? Okay. So there are 48 of 52. I'll wait a couple of more seconds. $49 of 52.
Hello, Professor.
Hey, Rajan. Yes.
The notes, can the notes be a PDF that we can download from Canvas? Because I tried some of the things that are like connected to Google Drives. Some of them can be when it's like in that thing, I was like able to access. I was able to access like the syllabus. Except then the other ones, it's like having this issue on my computer where it's like Google Drive is going through too many things to route to Canvas, so then it wouldn't allow it to work.
You should be able to download the material, at least if you access them. So you mean that like that embedded view is not working for you? It is not coming up?
Yeah, the Google Drive embedded doesn't work. It's not working sometimes. Sometimes it did, except for like the syllabus, except then all the other times where there's an embedded, it wasn't working.
That's strange. The classes may want to show, or if anyone has any idea.
Professor, what I've seen is sometimes if you are logged into Chrome with some other account and not your SJSU account, it doesn't work. But like if you're logged into your Chrome with your SJSU account, it will work. At least that's how it was for me.
So my setting is access level is anyone on the SJSU. So
yeah.
If you're trying to access it without your SJSU account, then you won't be able to. Rajan, maybe that may be the problem. Sometimes you log in with another private email or something.
I have 2 emails open on my browser, so it's probably like rerouting to like the email that isn't the SJSU one. So I'll try doing it with just the SJSU one.
Right.
See what happens.
Once you access it, you should be able to download that PDF. If you do not, then let me know. Right? Anyone else has already downloaded that material?
Professor,
I haven't seen. Oh, sorry. I can't. I don't think. I'm not sure if it's downloadable too. I don't see any downloading features on it. I can access the note like after I give it permission, and then the first time it asked me to go into my SJSU email, I did that, and then it let me see the notes. but it doesn't show me where I can download. I'm not sure if it's downloadable.
Okay.
If I may, there's a button. At least from what I'm doing is there's a button that goes to a new tab where you can view the PDF and download it from there. It's connected to the Google Doc that it's attached to.
Okay.
True, I see that too. Sorry, thank you.
Okay. So everyone got that from Matthew? What? Matthew, do you want to show it, share it in a screen and show it to everybody?
Yeah, sure.
Okay, let me open up the share screen. And I'm ending the polling and I'll share the results shortly, but let's Matthew go and share and show everyone how to download.
Okay. Sorry, I think you should be able to see my screen. Can you guys see the screen?
Yes, I see.
Oh, okay. So if I just click on the modules, that was what I was doing lecture 2, for example. Once it gets to this point, there's this button right here, pop out. And when you click here, over here next to the printing option, there's the download option. So you can download it like that.
Okay.
Okay.
Professor, I wanted to ask something. Did you purposely block the download for the solutions?
Yes.
Okay. All right.
Professor, I had a question regarding one of your announcements. So in your announcement, you mentioned if we join your waitlist before February 4th, we should be able to enroll for your course and see Canvas. Is that correct?
Yeah.
Okay.
Unless you need an ad code for some reason.
Okay. So the ad code's not necessary if we can get on your waitlist today and then just enroll like that.
Yeah, exactly. I think there are in this class, so you can register.
Got it. Okay, thank you. Oh, one more thing. Is there a Malc alternative to Model Sim? Because when I tried downloading Model Sim, it wouldn't let me because I think it's Windows-based only.
There are alternative tools. You can search in the Google, and in my lab 1, I have pointed out some. You can try them. Only point is that all our setup and simulation result are done with the Model Sim. So maybe it can create a problem. Like you did it in a different environment and submit that code to us, and we're trying to run it through the Model Sim. There may be little hiccups here and there if you do that.
Got it.
Other solution would be to use VirtualBox VM with a Windows on it and run that. I have another link to set up the Microsoft Cloud. I believe 2 semesters back, one student did it, and till then it worked for some people. And also what I heard, at least some hours are free for students from in the Microsoft Cloud environment. And you can loan a machine there, run your simulation job and do your work. That can be another route.
Okay, sounds good. Sounds like the easiest solution is just to use Windows.
Yes, that would be the easiest solution. Yes.
Okay, thank you.
All right, now let me share the results of this poll. So I see that 62% of the class said that all of them have reviewed lecture and read the lecture note, reviewed the videos. That's good, wonderful. The one you said, some of them, please try to pace up and complete those review before coming to the class so that that class discussion makes sense. And one said none. Maybe you are a student who doesn't yet have access to the Canvas. By the way, I have shared the materials directly to some of you guys who are waiting for that code through the Google Drive. So look at your Google Drive and see if those lecture materials are sitting there. And you can access to all the lecture videos in my YouTube channel. So you shouldn't you shouldn't have to fall behind the class. That's what I can comment on. And second is, have you noted your queries and corresponding discussion page? One says yes. I don't see your question so far, or you may want to ask me. And 36% said no. 62% said I don't have any question. That's strange. Basically, this is like if you don't have a question, that actually means two things. One is that you understand everything, or you have understand nothing. Okay, so I don't assume the first one, that you have understand everything that is being discussed in that module. So possibly the other point is true. So please go through that material and make sure that you have questions on top of that. Unless you critically think on that subject, on the material, understanding would be going to be difficult day by day. Okay, so please start critical thinking on every line, every paragraph of that reading material or the video talk or anything, and try to grasp the concept. And if you try to grasp the concept correctly, if you have many questions, that means you are going in the right direction. All right. So saying that, let me open up again for any questions, logistics or on the theoretical study, anything, or lab. Okay, then let me do one thing. Let me give you some review of how a computing system works. So from your CS47 or equivalent study, you should already have that concept, but let's brush up, okay, what we learned in that computer system studies in CS47 or equivalent. Okay, to do that, let me start this and share my screen first. Okay, all right. Okay, it's all set. Let's start with the memory, right? Memory is, you already kind of familiar with that concept and term, especially like when you try to buy a new system, a new laptop, you look at couple of specifications, right? What is the processor? What is the speed of the processor? I'll come to that speed part later. And then how much primary memory, or how much RAM, like in very, very quick term, you say, okay, this has 512 megabyte RAM, or this have 1 gigabyte of RAM, this has 8 gigabyte of RAM. This is the memory amount you look at the specification when you are deciding to buy a laptop or a desktop system. So that RAM you are talking of, that 1 gigabyte or 8 gigabyte RAM, whatever, that is the memory component of computing system, primary memory component, okay? And to model that memory device or memory component, we can simply think the memory is an indexed storage, just like an array, okay? So remember, like you use the array variable in your program, and you basically can access those arrays with the index values, like variable array A access at index 10, and you get the 10th element out of that, something like that, or 11th element, doesn't matter. But point is that this is very much, you can think this memory system is an indexed storage, and each index is, we call in the hardware world, is an address of that memory. Okay, so whenever you hear the term memory address, it's basically we are talking about that index in that memory indexed storage. Okay, so let's say a memory contains, for example, almost like 100,000 storage areas, like indexed from 0 to 99,999, and it contains values. So remember, like in computing system, there is nothing called like a string or sentence or word or a picture. Everything is a value. Even your high-level program is also a value in terms. When it converted back into the machine code, they're nothing but some values. Your picture, your videos, your forms, text, paragraph, everything is a value. It's represented by some value, and these values are stored in this indexed storage area, which we call a memory. Now at this point, let me introduce kind of an actor-act relation between this computing component to understand how a computing system works. So we introduce an actor, let's say we call it a MMU, or memory management unit. That's an actor, and together this MMU and this index storage together we call it a memory. Okay, so what it does in terms of functionality, you can tell a memory, hey, write value 5 at index 3, or in the hardware world we should say write value 5 at address 3, and it will happily follow that instruction and write the value at the address 3. Similarly, you can ask it write a value 13 at address 1. It will store that value 13 at address 1. Then you can say this guy as a, okay, read from address 1. So what it will do, it will return you back the value 30. It will read from that store and return the value to whoever is asking for that. So that's the memory in a nutshell. Question so far? All right.
Yes. Again? I'm sorry.
Matthew.
Yeah, what was MMU again?
Memory management unit.
Okay, thank you.
Now let me introduce the next actor. It's called ALU, or Arithmetic Logic Unit. It's a very simple actor which basically does perform all your arithmetic and logical function evaluation. For example, you can ask it, hey, what is addition result of 3 and 5? What is 3 plus 5? It will give you answer back 8. All right. Now, next actor in this whole computing system is called a register file and register file unit, which is practically is a model of memory. It is an index storage. Okay. And it just like the memory, it can read and write from and to the register storage, index storage. Difference is this, first of all, these components, this storage is much smaller in size. Like maybe there are 32 or 64 or maybe 128 to 56 storage, but nothing more than, I don't think it goes beyond 1K, like 1024. Like this is very rare. So this is limited in number. The storage is limited, very limited. And here memory can go up to your 8 gigabytes, 16 gigabytes, even 64 gigabyte for enterprise range machines. It can go beyond that as well as a primary memory or RAM, which is a huge, huge space. Whereas register file space is really, really limited. That is one difference. Other difference is that operation speed wise, register file is really fast compared to like blazing fast compared to RAM, compared to the memory that's sitting on the board of a computing system. So that's another difference. It is a very fast storage device, register file. There is one more operation difference, especially around the read. I will explain it later when it is needed. But so far, model-wise and function-wise, they're very similar, memory and register file. One is small amount of storage, but faster. Other is huge amount of storage, but slower. Now, next is introduce the big boss, controller. Okay, so this is the ringmaster, ringleader. This is the dawn of the whole system. This controls everything. Okay, it is kind of an, what is called in a music symphony, it's called conductor, right? Music conductor, who has this little stick and synchronize the music between different instruments. That's the analogy you can tell this is about the controller. Okay, this is one of the vital element in the computing system. And together, these three, ALU, controller, RFU, makes a processor. So if you take any processor like Intel, whether ARM or AMD, doesn't matter. At basic, it has these three components: controller, register file, ALU inside that. Okay, so that comprised of a processor. Question so far?
Yes.
Yeah, done.
So where is the list of instruction being stored? Is it stored in register file or it is stored in memory?
That's a very good question, Wang. I'll come to that. Just hold on, okay?
Quick question, Professor.
Yes.
So basically, when we say a faster processor or stronger processor, that does it just mean that it has more register files?
Not really. It means its operation speed is faster, which is related to another subsystem called clock, and we'll come to that later after this. In the next lecture, we will explain the clock system.
Okay.
All right, let's now proceed together. Now let's take a very one simple program like this. Simple initialization of a variable called A, 10, B, 20, and we compute the addition of them, C equal to A plus B. Right, this is a Java or C or whatever you want to think, that kind of programming. You have 3 lines, simple code. Now let's review how it is being executed with this simple model of a computing system with a one processor and one memory in it. Remember that each high-level variable is related to an address. It is assigned with an address. Who does it? Compiler. The tool compiler does that association. And let's say it, in this example, it associates the high-level variable A to the memory address 0, B to address 1, and C to address 2. And then also compiler does this thing. Convert this high-level program into low-level basic steps. Like you all know, it boils down to some assembly-level programming. Okay, so I haven't shown the assembly instruction yet, real assembly instruction. Just trying to break down these high-level program into smaller chunk of instruction that this whole system can execute. And this is at the assembly level. So it tells something like write 10 to the memory address 0, write 20 to memory address 1, then read from 0 and store it to register file 0, read from 1, store it to register file 1, and then fetch these 2 values, add them up, and then store the result into register file 2, which is this instruction. Register file 2 equal register file 0 plus register file 1, and then read from register file 2 and store it back in address 2. So simple, this simpler step that compiler broken down into an assembly code. Now comes the tool assembler. Remember, like 47, this assembly programming and all this stuff, you used assembler. The job of the assembler is to take this assembly program turn into some machine code, which is nothing but some numeric value. Remember, I told you that a program is nothing but some bunch of numeric value represented as numeric value. So here, assembler convert the assembly code into the corresponding machine code. And then these machine codes are going to be stored in the main memory. So I think one was asking that, like where this goes, this program. These machine codes goes into the main memory at some location and start from there, okay? So let's assume, let's expand this memory a little bit and store this machine code into that memory. Okay, it is let's load it. So whenever you start executing a program, first thing the system do is to load that corresponding machine code of the program into the memory. Okay, so let's assume for this very simple example, it loaded from the address 3. Okay, in real life, if you recall your CS147 study, in the memory, whole memory is divided into really chunk of parts. One is for the using the data storage, other distinct part for the code, or we call it a text segment, text storage, and so on and so forth. We're not going into that complexity in this example, but in real life, that's the happen. Like your whole memory address space is divided into chunk of different areas. Some areas used at a dynamic allocation, some used as for the stack allocation, some used for the static data, some part used as a text or the machine code loading. And they are predefined. Which part goes where? They're predefined and predefined by the systems. Like each processor and processing environment define its own memory space. Okay, so that is a part of the, by the way, the instruction set architecture definition that you will be going through in this lecture, lecture 1 as well. We are going to define this CS147 DV instruction set architecture. You will see we are defining this different segment, section, usage of the register, and so on and so forth. But let's not go into that complexity right now. Let's assume it just loaded into the memory, okay, from address 3. Now, to understand how things works, I need to introduce you to one more little component, important, small but important, which called a program counter or PC. What it does, it holds the address of the next instruction to be executed by the processor. Now, since this program is loaded from the address 3, your program counter should set to 3. And then this whole system start picking up instruction from the address 3 and start executing. Question so far?
Yes, Professor, I have a question.
Yes, Narinder.
Professor, we know that like ALU is made up of NAND gates and all the logic gates. Is it the same case with the controller as well? Is it made up of?
Yeah.
Okay. Is it possible to like how we did it in CS47 that we like implemented the ALU in assembly language? Is it possible to implement a controller as well?
Yes, you can pretty much. Even with the high-level language, you can. And in fact, we will be doing that in our projects, project 2, that will code a controller, which executes the program.
All right, perfect. Thank you, Professor.
All right. Yes.
So what relation do these numbers in the memory have to the instructions again? How are they mapping to instruction?
Oh, these assembly program to the machine code?
Yes. So that's machine code, the decimal format of machine code.
Yeah, this is a decimal format of machine. I just put some arbitrary numbers there for the example. Don't try to overanalyze this code. Okay, this is not tied to any processor or anything. Just what I'm stating is that it's only it is a representation, like it's represented by some values, this instruction.
Okay, thank you.
Professor?
Yes.
Would the PC be the same as the RIP register in the x86?
x86 RIP register.
Yes.
Yeah.
It's the same, right? Yeah.
I haven't programmed x86 for a long time. Maybe 20 years back I programmed it, so I forgot. Sorry for that.
Oh, that's fine.
Someone said anything like who has done x86?
I said yes.
Okay. All right, there you got your answer. Thank you very much.
Professor, just a little question. So is it only the controller that distinguishes between one kind of processor to other kind of processor? I mean, like ALU basically and the register file should be the same for all the processors, right? Is it just the controller that distinguishes like one processor from another?
You are right partially. So yes, controller is different for different processor, as well as the ALU. Like implementation technique of the ALU is a secret sauce of every processor company. You go to Intel, go to AMD, they have all the secret recipes for make a faster ALUs. Okay? So remember our discussion in our CS47. I think you were in my CS47, right?
Yeah, I was.
Right. So we outlined a generic implementation of the ALU there.
Yes.
But every processor company has different recipes to do that. Same with the register files and these components. They're pretty much trade secret for them.
Okay, I see. So like it's hard to tell that like what's different inside a processor because they are implemented differently.
Exactly. In the all theoretical classes, what we discuss is kind of a very generic concept that how things work at the very basic minimum level. But if we want to know, we got to know about the inside of the processor. You really need to join those companies and work in the processor team, processor design.
Okay, that must be really hard. Okay.
This is their $1 million or $1 billion business, right? No one is going to give you the secret out.
For sure.
So, all right, now let's proceed forward now. So we loaded the program into the memory. We updated the program counter to 3, and here it go, right? So this controller goes through different phases, and we'll formalize the phase later in the down the course. But let's assume it starts with the instruction fetch stage, where it basically picks up this address from the program counter and simply tell the memory unit, hey, read from this address. And memory return back that value, whatever that value is. At that point, after it receiving that information, controller goes into instruction decode state. And there it kind of parse out, break down these instruction into different parts and understand what a programmer trying to do there. Okay, the programmer trying to do simply write the value 10 at address 0. So it understands that at this point now. Now it goes simply issues this write 10 at address 0. It sends to memory, and memory writes that value to that memory location. And at that point, your program counter is also updated to the next instruction 4. So from this point, it's kind of pretty much repetitive pattern of action. Instruction fetch, read from 4, memory returns the value. Now process controller decodes that instruction, understand it's trying to do and write 22 address 1. So it issues that instruction to the memory, and memory happily writes that value into the address 1. And then program counter is updated to 5. Next instruction fetch cycle, read at 5, returns the machine code, the processor decodes it, and it says now it understands it's trying to read from address 0 and store to register file 0. So what it does as an action successively, it basically sends an instruction to the memory that, hey, read at 0, memory returns that value 10, then it instruct the register file write 10 at 0. So it receives the value, sends the value into the register file, and register file stored that value in register 0. And the program counter is updated to 6. This action goes on, instruction fetch, read from 6, returns the machine code, controller analyze it, And understand now I want to read from 1 and store it in the RF1, register file 1. So it issues the read at 1, get the value back. It asks to write that value into address 1 of the register file, and register file store it. Program counter goes to 7. Now it issues the instruction fetch, gets the instruction, decode it, and now it says, okay, I need to read from register 0 and register 1, add them up, and store that result back in register file 2. So what it does is do this, read from address 0 and 1. Now here is a little difference. Remember, in the memory, we can actually read from only one address at a time. But for the register file, it is possible to read from 2 addresses concurrently. So we can issue an instruction to the register file unit that, hey, read from these 2 different address together and give me the result back simultaneously. Okay, so with this instruction, register file actually sends back 2 values back to the controller, 10 and 20. And then controller sends this 2 value to ALU with an addition request. It's asking ALU that, hey, what's the addition of 10 plus 10 and 20? Give me the result back. ALU sends the result back as 30, and then controller picks that value up, sends to the register file saying that, hey, write 30 at 2. So register file unit stored that value in register 2. Program counter is updated to 8. Then the last instruction of this sample program become like this. It fetched from the memory, read at 8. So it issues that instruction to the memory. Memory returns that value, and controller decodes it and says that, oh, I need to read from register file 2 and store it at the memory 2, location 2. So it does send that instruction to the register file saying that, hey, read at 2. Register file sends back that amount 30 to controller. Controller sends instruction to the memory that write 30 at 2. MMU writes it. PC is updated to 9. And we are end of this program. Now you see that effectively what we did compute the result 10 plus 20. But almost explanation wise, it is almost like 20 minutes to explain this, what is going on. And believe me, this smaller step goes on into the processor, but very, very high speed. It is like nanosecond range. It's not even a microsecond range it takes. It's nanosecond range, very blazing fast. It goes, but nonetheless, it goes through all these steps, this basic step one by one. Question? All right, now let me show you like a little bit of real assembly program, especially in the MIPS language. The one will be kind of following, this is kind of a MIPS is a base of that CS147 DV. However, if you don't know MIPS, don't feel bad about that. We don't use the MIPS processor. We use the CS147 DV as our reference language. All right, so if I want to do this high-level program in assembly language, we possibly would write something like this. Okay, something like we involve the add I, store word, load word, etc. statement. Not important right now to understand really what is what, but I'm just trying to show you a sample look of an assembly program, how it looked like, which you probably already are familiar with, even if you have programmed with the x86 system. It goes something like this always. Question?
Professor, I have a question.
Yes.
So when we say like the processor works like in the range of nanoseconds, and since it's implemented on a piece of silicon, so like it works with electrons, right? Moving electrons. Is there any company that makes processor out of like fiber that's based on light, moving of light?
So this is light, like light moving and light, this thing that basically used in the communication. If you heard of the fiber channel or optics,
Yes, that's what I'm trying to ask. Is it possible to include that into a processor? Maybe that'll make it like more.
There are researches and university works going on with that kind of communication using the light or in general electromagnetic wave in the circuit. The challenges there is that in a small area, to control these sort of complex analog component, like it's not a clean digital signal, it's basically an analog component of your using an electromagnetic wave, and how to sense them, how to capture them, how to process them within the board, that's still in the research phase. Like theoretically, it has an endless possibility. We can speed up quite a bit about the processing, not in a commercial product yet. Except
I see, like
channel communication, where basically it's a different ball game. It's a wide range. You are basically sending data over several miles across the continent, under the sea. You have this light traveling through this fiber channel, and the other end you have these light sensors and receiver, which basically, depending on the intensity of the light you are receiving, it basically encode them digitally at that end and then convert into the electrical signals to send into the processors.
I see. Yeah, that's why I guess the quantum computers are still like based on probability of electrons.
Quantum computing is a little bit of different game. Like these, the one just I described when you asked about this, using the electromagnet to communicate between different component on board or on silicon itself, which basically a bottleneck nowadays, that electron movement of the electron and how much it takes time. That's a different ball game than a quantum computing that you are hearing that Google has one experimental. I believe Microsoft has announced recently one of them.
Yeah.
But it is all about, yeah, as you said, it's all about probabilistic state of an atom and how you can encode more than two state. Like till now, digital computer encodes state with just two values, 0 and 1. So quantum computing is about to encode more or pack more information in one quantum element. That is the ballgame there. And beyond that, I don't have expertise, okay, frankly speaking. I wish I know more, but I don't know.
Thank you, Professor.
All right.
Professor.
Yes.
Going back to the last example, when we do any operation in the area, does the computer always have to send like instructions and values from the RAM to the registers, or sometimes they go straight from the RAM to the ALU?
That's a good question. So if you are coming from the x86 world, which we'll study later as a complex instruction system computing, it is possible that your instruction encodes directly a memory address and operands come directly from the memory address.
Okay.
But in the world of RISC computing, reduced instruction set computer, which is example is ARM is one of them. MIPS is another example. They are all RISC category processor, which uses limited amount of instruction to access memory, like only load word and store word. These two instructions are there to access the memory. Every other thing is related to the register file and the ALU internally. It doesn't go through the memory at all.
Okay, makes sense.
So yeah, both of this camp has pros and cons, and I think towards after the midterm, we'll study a little bit on these two different categories of system, and we'll study what is the pros and cons of different such differentiation.
Okay.
All right. Thank you very much, Laura. That's a very good question.
Okay.
All right. Now, Okay, let's take 5-minute break. 8:14, 8:20s. We'll be back and we'll see what's next in our list. All right, let's get back to the business. Let us review a little bit, go over these lecture 1 components and see if you have more question on this. Please share. Okay. All right, so this is the lecture 1 that we are supposed to review, and let me also pinpoint some of the important things that you need to watch out there. One is this is like more generic discussions. Yeah, more important is that to understand these instruction set. Okay, so whoever coming from the x86 background, that assembly background, you possibly need to put more focus, more attention into these. The reason is that, like, if you are one of my ex-student in CS147, we used to deal with the assembly language for the MIPS processor, MIPS processor. And this instruction set is very much similar to that. It is the smaller scale of that MIPS assembly language set, with some twist there for our class fun, but it is more, you'll be more familiar if you are coming from my CS147 class. Saying that, this instruction set is not very much different than any other assembly language in a concept. So it has different type of instructions, and it describes the format and different field in the instruction, and then basically it goes and talks about the storage assumption and the memory segments, like what are my dynamic data area, what are my stack areas, what are my static data areas, text area, etc., etc. And also outline some of the usage of the register in this system. So that's there. And these 3 pages is probably the most important. These different instruction, set of instruction of different type, like R type, I type, J type. We classified the instruction in these 3 classification, and we try to describe what is their mnemonic, how to write the code, what is their operations there. And we also list down some of the all the opcodes and function codes of that instruction. So you need to understand that, and also understand how, given an assembly instruction, how to convert to the machine code. So here, go through one example like this, like let's say add R2, R1, R8 really means we are trying to read from register 1 and register 8, add them up and store it into the register 2. And with that respect, how do we generate the machine code for this assembly instruction? So you basically look up the opcode and put the bits there, look up the function code, put the bit in this field, and then fill out the rest of the field pretty much, and other fields, right? And once we do that, then we put together that 32 bits and convert into the hex code. So this is either binary representation of the machine code or the hex representation of the machine code. Now the question is, like, why it is important? First of all, I don't usually give machine code conversion problem in exam, because from exam perspective, it is not that important. However, remember, you have these 2 projects, project 2 and project 3, and in that you will be developing a simulation model of a processor, or in a nutshell, you will be developing a processor from very ground, very basic, like from scratch, you can say. You're developing a processor. Now, how to test that processor? You need to run some program, right? Some program, and there is no compiler assembler available for this toy processor, because this is, we define it. This is not a commercial processor. So you need to write down some basic assembly code with respect to using these instruction sets. and then convert them to the machine code of the program and load it into the simulation environment and test your processor, whether it is working or not. With that respect, it is very important that you understand how you actually can convert a given instruction into the machine code. Questions so far?
Yeah, Professor, RT, it's pretty much 8 in decimal. That's the 01000. The target register. Yeah, that one.
Oh, this one. Yeah, this is in the binary. So if you look at that RD, right, in this example, let's blow up the screen a little bit. No, it doesn't help. Anyway. All right, so let's look at this, right? So R2, so 2 is your, from the mnemonic, it is the RD, right? RD field goes this bit from 11 to 15, which is 5-bit long, right? So what do we need to do? Represent this number 2 in a 5-bit binary, which is like 000010. Similarly, R1, it goes, R1 is an RS, right? So it goes into bit from 21 to 25, which is again 5-bit. And that means 1, decimal value 1, I need to convert into the binary, 5-bit binary, which is 00001. Same applies to the RT, R8, which is 5-bit binary is 01000. So this number you are seeing here, representation, they're all in bits.
Perfect, thank you. Yeah.
Okay, so, okay, in this page, very crucial to understand this B equal B and E, these two, okay? And it's important that you understand how that branch address is calculated. So please make sure you understand that part. And you will see this has an impact when you actually implement a processor. The internal circuit actually depends on these assumptions. You will see that. So this is important, branch instruction to understand that, as well as these two instructions, load word, store word. They're also important in the sense they are the only two instructions that can access memory. So please understand this instruction as well. And we have jump, JL instructions. They're kind of a jump, or like jumping from one code place to another instruction, and so on and so forth. They're not interesting, much similar to the MIPS processor. Okay, these two are interesting. Push and pop. MIPS doesn't have it. I just introduced it for fun. Okay, just to show you, when you introduce a new operation in this operation set, instruction set, how it changes your circuit, internal processor circuit. We'll discuss that around, I believe, lecture 11. Okay, so we'll see how we make a circuit, build a logic circuit to accommodate push and pop instruction in this instruction set. So this is kind of a fun and important tool to study with. Okay. Then we went into that, introduced to ourselves this different organizational component. Just this is a review of your computer systems class. Like there is an ALU, what is function, what it looks like, how we can make an interface diagram or schematic diagram, something like that. So that's the end of this lecture 1. Question?
Yes. What is the purpose of the immediate instructions?
Immediate instructions?
Yeah.
Okay, so it's one operand is your immediate type. Like you don't involve a register, but you are basically introducing and value directly into the I type. Now, what is the reason of introducing that? Why cannot we simply have the register type? Okay, Just think, when you start writing an assembly program, just think when you did it in your CS47 or equivalent class, how do you initialize the register through the program? That is one example I'm giving. Like it's basically how at the power up, when you power up the machine, your register contents are all 0. And you want to start with some value in your algorithm or the high level program that you are trying to implement. You need some concrete value, let's say 100 into one of the register. How do you put it there? With a register only operation, you cannot do that, right? Similarly, like memory, if you think of the memory side, memory also on power up, everything is 0, right? And when you start a program, your program is loaded. You can load the static data section through the loading, but again, that goes through also a bunch of instructions, right? When it's a boot up instruction, right? And those boot up instructions also need to instruct these memories to, hey, load this, that, etc., etc. So there is a specific need of having the argument defined within the machine code itself, the argument value defined within the machine code itself in different programming scenario. And that's why this I-type instruction set has been introduced. Make sense, Hogan?
Yes.
Okay. Now, then we move to the next lecture, which is, let's preview that what is there. So we'll continue this study of like introducing ourselves to the, or it's a refresher course again, like to what is the different, oh, that's not the one I want to load. Where is that? Oh, lecture 2 here. So it's basically all the rest of the system, like clock system, memory, controller. There is a little bit introduction of von Neumann architecture, system software. It is a little bit bigger lecture. It has different, like 5 parts of the video. Please make sure you watch them. And let's go through like what there. Like we start with the clock system, which tells you the concept, why we need a time reference between these components and what provides that time reference. So that's the study here. And we, in that process, will introduce ourselves to different parameter in the clock, like a time period, frequency, duty cycle, rise time, what is that? T rise and T low, time to rise and time to lower down that logic. Those kind of information and definition we'll go through. Then we'll study about the memory system model. So we are not going to study about the real hardware here. It is more like a conceptual study that what a generic memory system looks like. And we introduce one of the memory systems here and their operation with respect to the timing diagram. So you need to understand this, what is a timing diagram and what it represents. How do you read? If you look at the diagram, how do you read? And how do you interpret these diagrams? That you need to make sure you understand that. And also put a special emphasis on an observation that in this model, in this system, we cannot issue a back-to-back read and write operation. Like let's say I request a read operation to the memory. In the very next time cycle, I cannot just issue another write cycle. I need to wait one more cycle after that. So please make sure you understand that phenomena. That is very important. And that understanding will be needed for doing some of the problem, like mathematical problem that has been introduced in the problem set. So make sure you understand that concept. And from there, we try to derive the register file. Okay, so remember, like I said, the register file model is very much similar to memory model, but here we start with the memory model and then we go in a direction that to build up a register file model very much similar to the memory model and bifurcate the model from there for much efficiency. For example, how can we read two registers together simultaneously from one component, though it is act like a memory. So we derive that. So we start from the memory model and step by step derived into a register file model out of that. Okay, and then we introduce ourselves a little bit on the control system, how it interacts with the other component, and how it goes through the different cycle. And this is very important, and probably we'll live through these 5 cycles: instruction fetch, decode, execution, memory, and write back till end of the semester. Okay, so you start here, we'll keep on like meeting this cycle, execution cycle of an instruction till the end of the semester. So this is very important concept that please pick that up from here. And then we talk about some generic of the von Neumann architecture. It's a very generic concept. And then we went on to the Hubbard architecture, why it is pros and cons. We'll discuss a little bit on that. And then we touched base on the system software, their roles in the whole computing system. And hopefully you will be getting more insight into system software in your operating system class and your language study class. Or I don't know if there is a specific compiler class or not, but maybe it is a language study. But these two will should give you more detailed insight into the system software. So we'll just touch base and try to kind of relate between system software and architecture, where it connects them together, how it works in a synergy in a computing system. That's what our target is. Question? Okay, then if there is no question, then let's stop at this point. Good night, everybody, and see you on Thursday.